All right, hello everybody. So today we're talking about equations of lines and planes, specifically in 3 dimensions. So first, let's say in 2D, 2 dimensions, a line is determined by a point on the line and, sorry, but not to say here, by a point on the line and the direction of the line, which we can say is its slope or angle of inclination. Okay, and then the next step would be to say that then we can write the equation of the line using point slope form. Okay. Now we need to move to 3 dimensions. So I'll say in 3 dimensions, a line L is determined when we know a point P0, coordinates x0, y0, and z0 on L in the direction of it. Right, so it's the same thing. But the difference is whenever we're talking in 2 dimensions, we get to determine the direction just from the slope of the line. That's not necessarily the case in 3 dimensions. So the difference here is that the direction of L is described by a vector v that is parallel to L. And if R0 is the position vector of P0, and so if this is the position vector of P0 and R is the position vector of another point, let's say P with coordinates x, y, and z on L, so we pick another point on the line, then we must have Alright, so before I finish the statement, let's just gather exactly what's going on here. So let's draw a coordinate system. So let's say this is our coordinate system, and this is our line L. Let's say that's the line L. And let's say that we pick a point on the line. I don't know, let me use orange, let's say. Pick a point on the line that's P0. That's the starting point. So that's P0 with coordinates x0, y0, and z0. And we pick a second point on the line. Let's say this is the point, I don't know, P, which has x, y, and z as its coordinates. Then we said here that r0 is going to be the vector from the origin to P0. So this is r0. So it's the vector r0. It's a little bit hard to read there, but that's r0. And the second vector that we labeled here was the vector r, which goes from the origin to the point P. And if we connect the 2 points, so let's say we connect the 2 points here, let's call this vector A, where we connect the 2 points. So that's the vector, the position vector from between P0 and P. And we said that V is going to be some vector parallel to the line. So some vector parallel to that vector. Okay. So let's just write down what we have here. We know that R, the vector R, is going to be equal to the vector R0 plus the vector A. Right, so if you look at what you're doing there, you add R0 plus A. Remember, we add this vector onto the tip of that vector, and then the resultant vector here is now R. So you can see that, in fact, this is true. R is equal to R0 plus A. And, or another way of writing it is that R equals R0 plus T times V, where T is some scalar, right? So V we said was parallel to the line, so if you multiply this vector by some number, just scale it up by some amount, then you're going to get the vector A. So we can replace A with T times V, where T is a scalar. Okay, remember a scalar is just a number. Okay, and we can also say here, as T varies, the terminal point of R, remember the point at the end of R, the terminal point, traces out the line L. Right, so you can actually get all the points on L just by looking at the endpoint of this vector for all different values of T. Okay, and I'll say here, note positive T corresponds to, so if T is positive, then it's going to be points to the right, because we're starting with our vector R0, and we're adding some amount along this line to get the resultant vector, right? So we're just moving our vector R to the right as A gets longer, as A grows to be a bigger positive number. So we're just moving to the right. So we're getting all the points, the terminal points are going to be all the points to the right of P0. So here, positive T corresponds to all points on L that lie on one side of P0, And while negative t corresponds to the points on the other side of T0. Okay. And now, let me erase the left word here. Let's just describe what's going on in terms of vector components. So let's say V is equal to the vector with components A, B, and C. And R is equal to the vector with components X, Y, and Z. Remember, R is just the position vector of this point, and remember the way we turn this into a position vector is we take the same coordinates and just turn the point into a vector, and that's going to be the position vector R. Okay, and if we wanted to write R0 out, then we would do the same thing. It would be x0, y0, and z0, because those were the coordinates of the point P0. Okay. Then what we can now write is, well, we know the equation we wrote down on the left, or on the right there, was R equals R0 plus T times V. So that'll become, so if we just expand out, so we just plug in what we know for each of these. If we do that, then we're going to get X, Y, Z. Remember, that was equal to R. And then we plug in R0 and V. So if we do that, we're going to get X0, Y0, Z0 plus T times A, B, and C. Okay. So now we can distribute. So remember here, this thing here was R. This thing here was R0. And this thing here, sorry, that's T. This thing here was our vector B. Okay. And now let's just go ahead and combine everything. So if we do that, then on the right side here, if we distribute T, then we leave this one unchanged. But if we distribute T, then we're going to get A times T, B times T, and C times T. Okay. And now we can just add together these two vectors, and we're going to get x0 plus t times A, y0 plus t times B, and z0 plus t times C. Okay. And now we can just, well, the x-coordinate of this needs to be equal to the x-coordinate of this. So if we just combine all of that, then we get the equations x equals this x-coordinate, x0 plus t times A, and y equals y0 plus t times B, and z equals z0 plus t times C, where t is a real number. Right, so this notation, this might look confusing. This just means that t is in the set of real numbers. That's how you would read that. But this is just saying that t is some real number. So don't worry about this. It's just saying t is a real number. But we actually get these three equations to figure out exactly points on the line using the original point and the coordinates of this vector v. And then t is just some real number. So we can actually get those. So I'll call this, let's call this equation 1, equation 2, and equation 3, right? So what we can say here is that equations 1, 2, and 3 are the parametric equations of the line L through the point x0, y0, and z0 that is parallel to the vector A, B, and C. Those are vector B. Right. So we can actually, we have a name for these. They're called parametric equations of the line L. Okay. So here, of course, we would say that t is the parameter, and each different value of t is going to give you a different point on the line, right? So if you just wanted to find a different point on the line, you would just plug in a different value for t, and that would give you a new point on the line. So that's why they're useful. So let's go ahead and do an example using these equations. Okay. Example number 1, we're going to say find a vector equation. So part A is going to say a vector equation, and part B will be parametric equations for the line passing through the point 0, -3, 8, and parallel to the vector 3i plus 12j minus k. Right. So this gives us a line, because if we have a something that's going through this point and it's so the line is going to be parallel, or sorry, it's going to pass through a point and it's going to be parallel to some vector. So this gives us a line. And part A says to find, so let me write down, this is part A and this is part B. But part A still says that we need to find a vector equation. And now, remember what I said earlier, is that the way we find a vector equation is we need to find R equals R0 plus T times V. Now, if we look at what we're given, these are going to be the coordinates of R0, but we need to turn this into a vector. So we'd say that R0 equals, so the vector R0 is going to be equal to 0, -3, and 8, right? And here, this is going to be V. So V is going to be equal to the vector with first component 3, second component 12, and third component -1. Right, so that's just from reading this. So that's going to be our V, right? Because V is the thing that it's parallel to, and R0 is the position vector of the point that the line passes through. So that gives us what we need in order to plug it into here. So we're going to get an equation for R, and remember R is the way that we find all of the different points on the line. So that's why it's important. So let's just plug in what we know. We know R0 is 0, -3, 8, and we have T times V, which is 3, 12, and -1. Okay, so now we just have to add these together. First we distribute T, so we're going to get 0, -3, 8, plus T times, we distribute T. So if we distribute T, we're going to get 3T, 12T, and -T. Okay, and now we just need to add the two vectors, so we add the components. And if we do that, we're going to get 3T plus 0, which is 3T. Here we get 12T minus 3. And for the third component, we get 8 minus T. Okay. And now, notice this is our x coordinate, our y coordinate, and our z coordinate. So this is our vector, but we can go ahead and write down the equations of this vector. The x component is 3t, the y component is 12t minus 3, and the z component is 8 minus t. So these would actually be our answer, right? Because these would be our equations for the vector. Okay, and now parts, that's not what I meant to say. This is our answer to part B, right? These are the parametric equations because they depend on t. That's what I meant to say. These are the answers for part B because these are actually parametric equations. They depend on t. Our answer for part A, so this is our answer for part B. That's what I meant to say. Our answer for part A will either be one of these two. WebAssign is going to accept either of these two as answers. So we'd say that either of these two is part A. Okay, so this is our vector equation, and this is going to be our parametric equations. And part C, we're going to introduce part C now. Part C is going to say find two other points on this line. Right, and this is why this is actually a useful thing, is because this gives us this vector, and using this vector, we can determine all of the points on the line just by plugging in different values of t. So we just have to choose two values of t and plug them in. So I'll say here, all we have to do here is choose two values for t and plug in. That's all we have to do. So it doesn't matter what values you choose. I'm just going to pick some nice values. I'm going to say, first we're going to pick t equals 1. Okay, so that's the first thing we're going to do. And remember, we just plug it into here. So we just plug in t equals 1 into here. So we're going to get 3 times 1. Remember, I'm writing parentheses here because this is a point, not a vector, right? Because we're finding points. So plug in t equals 1. So here we're going to get 3 times 1, 12 times 1 minus 3, and 8 minus 1. Right. And if we go ahead and simplify that, that's going to be 3, 9, and 7. So that's another point on this line. So that's one of our answers. And let's just pick another value of t. Doesn't matter what we pick. I'm just going to pick -1. So if we plug in -1, we're going to have 3 times -1, 12 times -1 minus 3, and 8 minus -1. Okay, and now if we simplify all of this, we're going to get -3, -15, and 9. Okay, so this would be another point on our line. right? Because as long as we pick a real number for t and we plug it in, then it's going to give us a point on the line. Okay. So let's write down another thing over here. So we've finished the problem. So we figured out how to make vector equations of the line and parametric equations of the line. Let's see one more type of thing. If we solve for t in each of the parametric equations, and set them equal, we get the symmetric equations. Okay. So if we write down the symmetric equation, if we write down the parametric equations, that's what we solved earlier. So x was equal to x0 plus t times a. Y was equal to y0 plus t times b. And z was equal to z0 plus t times c. Okay. Now, what we said here is we're just trying to solve these equations for t. So if we do that, we just solve all these equations for t, then this is going to become t equals x minus x0 over a, right? So you subtract x0 on both sides, then you divide a on both sides. That's what you get if you solve for t. Here we solve for t. T equals y minus y0 over b. And here we solve for t. So we're going to get t equals z minus z0 over c. Okay, so t is equal to this, t is also equal to this, and t is also equal to this. So all three of these things are actually equal to each other. And that's why we call them the symmetric equations, because they're all equal to each other. So x minus x0 over a equals y minus y0 over b equals z minus z0 over c. And we call these the symmetric equations. Okay. And notice here when we were solving for these, we were dividing by a, b, and c, but those could actually be 0, because remember those were the components of the vector v. Some of those could end up being 0, so you have to be a little bit more careful. So observe. If a equals 0, or b, or c, then, so if a equals 0, then, so if you look here, if a equals 0, then x equals x0, which means L lies in the vertical plane x equals x0. Okay. And I'll say here, in this case, the symmetric equations are, so we would write x equals x0, comma, y minus y0 over b, and, comma, y minus y0 over b equals z minus z0 over C. So remember, we couldn't say this because A is actually equal to 0 and it doesn't make sense to divide by 0. So instead, we say this. And those would be the symmetric equations there. Okay, so let's actually go ahead and find these symmetric equations in an example. Okay. So, example number 2 is going to say P is the point 2, 5, and 4, and Q is going to be the point -1, 5, and 0. And it's going to say find. Part A is going to be parametric. And part B is going to be symmetric. Equations for the line passing through P and Q. And part C, so we have part A and B. Part C says find the point where the line intersects the XY plane. Okay. So notice here for part A, we were not given a vector parallel to the line. Remember, so what we needed was a vector v that was parallel to our line in order to solve for the parametric equations. Well, we're not given v. But what we can say is, well, if we have a vector going from P to Q, then that's a vector that lies entirely on the line, so it should be parallel to the line. So what we can do is just find the vector from P to Q, and that can be our vector v. So I'll say here, but the direction vector PQ, right, so this is the vector from P to Q, is parallel to the line. So we're going to set V equals the vector PQ equals, now we just have to calculate what that is. So remember, if we're trying to calculate a vector between two lines, or sorry, between 2 points, then we take the coordinates of the second point and subtract the coordinates of the first point, right? So we take the x coordinate here, and we subtract the x coordinate here. So we're going to have -1 minus 2. Second coordinate would be 5 minus 5, and the third coordinate would be 0 minus 4. Okay, so if you go ahead and do the calculation there, that is -3, 0, and negative. And that's going to be your, remember we labeled these as A, B, and C. So those are your values of A, B, and C. Okay. So notice here we can either pick P or Q to be our point P0. Let's just go ahead and pick P to be P0. So I'll say here if we choose P equals P0, so you could choose Q to be that point, but it didn't matter. So we'll just pick P to be the point P0. Then R is going to be equal to, so remember we said it was the coordinates of P0, so it's going to be 2, 5, and 4. That was our vector R0, the position vector from, sorry, the direction vector from the origin to that point. That's going to be that, plus T times our vector V. So we've said our vector V was -3, 0, and -1. Okay, so now we just have to solve what this is equal to. This is 2, 5, and 4 plus -3t, 0, and -4t. Now if we go ahead and add these things together, we're going to get 2 minus 3t, comma 5, comma 4 minus 4t. Okay, so for part A, we can go ahead and say, part A, we need the parametric equation. So this is our x coordinate, our y coordinate, and our z coordinate. So we can just write that. So x equals 2 minus 3t, y equals 5, and z equals 4 minus 4t. Those are our parametric equations. So that's already our answer there. Part B asks for the symmetric equations. So let's go ahead and write that. Remember, these were our symmetric equations. Okay, so for part B, we'll write out our symmetric equations. You can check. I'd encourage you to do it, but you can check your answer. Would be x minus 2 over -3 equals z minus 4 over -4. And remember the y coordinate, since b, so here b is equal to 0. Since that's the case, we need to write separately that our y coordinate is equal to 5, which is what we wrote down here. Okay, so that would be the answer to part B. That would be our symmetric equations. And now part C says find a point where the line intersects the xy plane. So remember, z is equal to 0 on that plane. So a line intersects the xy plane exactly when z equals 0. So we can set z equal to 0. So we're just going to set z equal to 0 here. And if we do that, we're going to have 0 equals 4 minus 4t. So if we solve that, we're going to get the t equals 1. And remember, the way we find points on the line is we just plug in values of t into our parametric equations. So we already know that exactly the value of t we need is 1. So we just plug in t equals 1 into our parametric equations, and that's going to give us the point on the line that we need. So when t equals 1, we're going to have x equals, so we just plug in 1. So we're going to have 2 minus 3, which is -1. Y is always equal to 5. And z is going to be equal, well, we said it's going to be equal to 0 because it's on the xy plane. So the line intersects the xy plane at the point, and the point would be -1, 5, and 0. Okay, so that would be our answer. All right, so we've got one last topic to talk about here because remember we talked all about lines, but the title of the section was lines and planes. So we need to still talk about planes. Let me put the board here. So for planes, what we can say is we can describe a line in 3 dimensions using a direction vector but this is not enough to describe a plane. Okay, so think of the floor and the wall, right? Those are 2 planes. The place where the floor meets the wall is going to form a line, right? So you can see a line where the floor meets the wall. This line is going to be parallel to both the floor and the wall, but a line that's perpendicular to the wall wouldn't be actually perpendicular to the floor, right? Because let's say you have, say this is your floor and this is your wall here, then a line perpendicular to the floor, let's say, or a vector, it's a line, but so let's say we have this that's perpendicular to the floor. Well, that's actually going to be parallel to the wall, so it's not perpendicular. So line that's perpendicular to the wall wouldn't be perpendicular to the floor. So what we're going to do to differentiate planes is to say, to describe a plane, we use a point P0, coordinates x0, y0, and z0, and a vector n, called the normal vector that is perpendicular to the plane. Right, so I drew a vector here that's perpendicular to the floor, and notice that vector is actually parallel to the wall, so it is actually different, right? So that's going to be a way of differentiating planes, or telling which plane is which, is saying, well, the normal vector for this looks different from the normal vector for this, because the perpendicular vector to this plane would look something like that. So we pick a point on the plane and a vector that's perpendicular to the plane, and as long as you have those two pieces of information, you can actually determine exactly the plane you're talking about. So let's actually draw a bit of a better picture here. Let's draw a picture. And remember, whenever we're drawing our coordinate systems, we need to remember that we need to use the right-hand rule. So if we curve our direction of our hand in the direction of x and y, then we should get the z direction. So it should be x, y, and z here. Right, so it's actually important that you draw your coordinate system like that. But if that's our coordinate system, let's go ahead and draw the plane that we're talking about. Say, this is going to be a bit hard to draw, but let's say that that's the plane that we're talking about. And let's draw some dotted lines where this is going through the coordinate axes. and it's going over the x-axis, so it's not going through that one. And let's draw 2 points on this plane. Let's draw a point here. We're going to call it P0. And let's draw a point here. We're going to call it P. And we can draw the vectors that we were drawing earlier. Remember this vector from here to here. That was R0. And the vector from here to here, that was R. And we can draw a vector between these 2 points like this. Okay. So I'll say here, again, R0 is the position vector of P0, and R is the position vector of some arbitrary point on the plane and here I'll say that the vector equations of the plane, let's write them down. 2 are going to be the n dot with r minus r0. So let's think about what that means first. Okay, so r minus r0, that's going to be, well, you put the tip of r0 at the tip of r, and you connect the base of the 2 vectors, well, it's parallel to this vector that I drew here. So this is actually r minus r0. It's the vector between P0 and P. Now, if you take the dot product of that with what we said was the normal vector, so the normal vector is a vector that's perpendicular to the plane, so it exactly sticks out of the plane, that's n, our perpendicular vector, our normal vector. So if you take the dot product of this blue vector with this red vector, well, notice the 2 vectors are perpendicular because this is a vector on the plane, this is a vector perpendicular to the plane. Now, if you take the dot product of 2 perpendicular vectors, that always gives you 0. So our vector equation here is going to be that this is equal to 0. Now, if you actually expand that, take the dot product, if you actually do the work there, then you're going to get this is actually representing the same thing as the equation n dot r equals n dot r0. Okay. So those are what we call the vector equations of the plane. So for the next thing here, let n equal the vector a, b, and c. So let's say that that's our normal vector this time. R equals the vector x, y, and z. And R0 equals the vector x0, y0, and z0. Okay, then n dot r minus r0 equals 0 is equivalent to, and let's just plug in what we know for n, r, and r0. So if we plug those in, we've got the vector a, b, and c dotted with the vector x, y, and z minus the vector x0, y0, and z0 equals 0. Okay. And notice here we just we subtract the 2 vectors. We're going to get a, b, and C, dotted with the vector x minus x0, y minus y0, and z minus z0. Okay, and now we can just go ahead and take the dot product. Remember, when we're taking a dot product, we just multiply the components. So we multiply the x components, plus we multiply the y components, plus we multiply the z components. So if we do that, we're going to get a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And now we actually have a name for this equation. This is the scalar equation of the plane. Right, so we have our vector equations of the plane, and we have our scalar equation of the plane. So now we can go ahead and do exercise number 3. Okay. Find an equation of the plane through the points P, which is going to be 1, 3, and 2, Q, which is going to be 3, -1, and 6, and R, which is going to be 5, 2, and 0. Okay. So remember, in order to write our equation, we need to figure out what n is equal to. Because we need to write this, so we need to know what n is equal to. So we need, right, because here we need a, b, and c, and those are the coordinates of n. So that's why we need n. So we need n to write an equation. Both PQ, so the line from, the vector from P to Q, and the vector from P to R lie in our plane. So these are two vectors in the plane. And notice if you take two vectors and you take their cross product, then that's going to be a vector that's perpendicular to those two vectors. So that vector is actually going to be perpendicular to the plane. So that's what we're looking for. So since PQ cross PR is perpendicular to both PQ and PR, we can take, so we just need to find some vector that's perpendicular to the plane. So we can take our normal vector to be equal to PQ cross PR. Okay, so we can go ahead and do that. So now we've just got to figure out what the vectors PQ and PR are equal to. So let's first do PQ. PQ is going to be equal to, so remember you take the x-coordinate of the second point and you subtract the x-coordinate of the first point. So it's going to be 3 minus 1. Next you would have negative 1 minus 3. And lastly you would have 6 minus 2. Okay, and if you do the math there, you're going to get 2, negative 4, and 4. So that's the vector from P to Q. Those are going to be its coordinates. And similarly, you can take the vector from P to R. Remember, you take the coordinates of R and you subtract the coordinates of P. So you're going to get 5 minus 1 and 2 minus 3 and 0 minus 2. So if you do the math there, you get 4, negative 1, and negative 2. Okay, so we figured out our two vectors, and now we need to take their cross product. So remember the way we do that is PQ cross PR equals, so the way we do that is by taking our determinant, where our first row is the vectors I, J, and K. Remember those are unit vectors in each of the directions. So this is the unit vector in the x direction, in the y direction, and in the z direction. So those are our unit vectors. Then we write out the coordinates of PQ, 2, negative 4, and 4. And lastly, we write out the coordinates of PR. So 4, negative 1, and negative 2. Okay, so now we need to take this determinant. And now the way we do that is by taking each subdeterminant. So remember, we get rid of the first row and column. So we're going to have I times the determinant negative 4, 4, negative 1, negative 2. Then we subtract J times the second determinant. So we get rid of the first row in the second column. So we're going to have 2, 4, 4, negative 2, and plus K times the determinant. Now get rid of the first row, the third column. So we have 2, negative 4, 4, and negative 1. And remember the way we do these 2 by 2 determinants is we take the first diagonal and we subtract the second diagonal. So we take negative 4 times negative 2 and then subtract 4 times negative 1. Okay, so if we do all of that, we're going to end up getting 12 times I. You can check my work here. We're going to get 12 times I plus 20 times J plus 14 times K. Okay, so that's going to be our answer there. And now we can just write that in vector form. So we're going to get that n equals 12, 20, and 14. Okay, so those are the coordinates of n. So these are A, B, and C. And then we can write down both the vector and scalar equations of the plane. Or I'll skip, you can write out the vector equation of the plane if you want. I'll skip that, but I'll write the scalar equation of the plane. The scalar of the plane is, so remember we had a formula for it. It was A, which is 12, times x minus x0, which is 1. Remember, x0, y0, and z0 are the coordinates of P. That's what we chose. So we're going to have 12. This looks like an R. This is a 12 times x minus 1 plus 20 times y minus 3 plus 14 times z minus 2 equals 0. So that's our scalar equation of the plane. And now if we want the linear equation of the plane, all this means is we're moving all the constant terms onto the right side. So if you distribute and move all the constants to the right side, then the answer you're going to get is going to be 12x plus 20y plus 14z. And you move all the constants to the right, the answer you're going to get on the right is 100. Okay, so that's the linear equation of the plane. This is what you're kind of used to seeing, and this is kind of maybe not what you're used to seeing, but this is going to be the scalar equation, this is the linear equation. Okay. Now, the last thing we need to talk about is distances. All right, so distances. I need a different color here. Distances. Okay, so let P0, coordinates x0, y0, that's poorly drawn. X0, y0, and z0 be a point on the plane described by ax plus by plus c times z plus d equals 0 with normal vector n equals coordinates a, b, and c. Okay. If P1 with coordinates x1, y1, and z1 is any point and B, vector B, is the distance, that's not right, is the vector from P0 to P1, then the distance D between P1 and the plane is given by, so our formula is going to be D, our distance, is equal to the size of the component of B that's in the n direction. And remember, we actually had a formula for this, and our formula is going to be the size of n dot B over the size of n. Okay. So we actually have a formula just exactly to figure out the distance between the point and its closest neighbor on the plane. And we're going to use this to derive another formula. So the distance D from P1 with coordinates x1, y1, and z1 to the plane ax plus by plus cz plus d equals 0 is, so our formula is going to be d equals the size, sorry, not size, the absolute value of ax1 plus by1 plus cz1 plus d. So remember x1, y1, and z1, those aren't variables, those are coordinates of this point. So if you add all this stuff together, this is giving you a number, and we're taking the absolute value of the number, over square root of a squared plus b squared plus c squared. All right, so we actually have a nice formula to figure out the distance where we don't actually have to deal with the vectors. So that's pretty nice. So our last example today. Our last example is number 4. Again, that's that color. Number 4. We're just going to say find the distance between parallel planes So one of the planes is going to be 10x plus 2y minus 2z equals 5, and 5x, so the second plane is 5x plus y minus z equals 1. Okay, so what we need to do is choose a point on both of the planes. So first thing here, so the first step, maybe I'll write in a different color. So the first step here is to choose any point on, and what I meant to say was on either plane. Right, so what I meant to say is we just need to choose a point on one of the 2 planes. So I'll choose y equals 0 equals z on the first plane, which gives the point 1/2, 0, and 0. Right, so we just needed to pick a point on the plane, and if we plug in y and z equals 0 into this function, then we're going to get that x is equal to 1/2. So that's a point on the plane. Okay, and second thing I'll say here is for 5x plus y minus z equals 1, this plane has normal vector n equals 5, 1, and -1. So what we can do here, so we have a normal vector to this plane. We have a point that's not on the plane, so that's our P1 over here. And now we can just go ahead and use this formula. So the distance is going to be equal to the absolute value of, we just plug in everything we know, right? This was our A, B, and C. So 5, 1, and -1. So we're going to have the absolute value, and notice here D is going to be -1 because if you move the D over to here, you're going to get, because this was our formula here, and here if you subtract d to be on the other side so that it's actually equal to 0, you're going to get d is negative 1. So let me just write all that out. A is 5, B is 1, C is negative 1, and D is also equal to negative 1, just by looking at this equation and comparing it to our formula up here. Okay, so we figured out all those values, and we know our point. This is going to be our x1, y1, and z1. So now we have everything we need to just plug it into the formula and get an answer. So we're going to get 5 times a half plus 1 times 0 minus 1 times 0 minus 1, the absolute die, over square root of 5 squared plus 1 squared plus negative 1 squared. And if we take this, we're going to end up getting, after we simplify a bunch, we're going to get 1 over 2 times root 3. That'll be our answer. So that's the distance between these two points. Okay. And the reason why it didn't matter which point we picked on the plane as P1 is actually the fact that they're parallel. So if you imagine two parallel planes, let me draw two parallel planes. This is getting difficult. Sorry. Let me draw two parallel planes roughly. Okay, so imagine these two are parallel, which it's kind of hard to see that, but what that means is no matter which point I pick on the green plane, its closest neighbor is going to be exactly the distance between the two planes. If these planes weren't parallel, then it would actually matter which 2 points you picked, because let's say you have a plane that looks like this, and a plane that actually, I don't know, looks like this. Maybe it's a different color. Let's say we have a plane that looks like the blue plane and a plane that looks like the red plane. Then if I picked a point way up here, then its closest neighbor on the blue plane is right here. So this is actually the distance between the 2 points. But if I instead change my choice of point for P1, let's say I pick P1 to be here, then its closest neighbor on the blue plane would be right here, which is a much shorter distance. But the fact that these two are parallel means it didn't matter which point I picked for P1, and you can just use the normal vector for, so this was our plane that we picked, and this was our P1, and we picked the normal vector to this plane. And notice they're parallel, so actually they have the same normal vector for the 2 planes, and everything just works out. So the only reason this worked out is because they were parallel. So that's important to note there.